Now we will talk about the divergence theorem of Gauss. The divergence theorem of Gauss allows us to evaluate a triple integral over a region in the space named T that corresponds to this evaluation. So we are trying to evaluate the divergence of a vector function f over a region T in the space. However, we can also write this integral as a surface integral of the given vector function f multiplied by the normal vector of the surface multiplied by the derivative of area. So we have a region in the space T in the xy z plane or space, which would be better. So this region in the space that is dependent on these three coordinates that corresponds to a triple integral can now be mapped to a surface integral that's also in the xyz plane or space, but we will, as the integral is a double integral, we will only consider the rate of change in two coordinates of the space, allowing us to make an easier evaluation of the given integral. So another form of writing this triple integral would be the partial derivative of f1 over x, of f2 over y, and of f3 over z times dx, dy, and dz. So this allows us to rather evaluate this triple integral in an easy way by only making a surface integral, or vice versa, evaluate a surface integral as a triple integral that maybe would be even easier than the first one. Another important topic that we would be talking about now is the Stokes theorem that is kind of similar to the one we previously talked about. This kind of integral allows to evaluate a surface integral of the curl of a given vector function as a line integral of a closed curve C f times the partial derivative of r s ds. So now the importance of this theorem is that it allows us to evaluate a surface integral as a line integral of a given closed curve. So it's easy, or maybe this will make the evaluation of this surface integral easier, and we can also write it as this. So we will have n1 plus f1 over z minus f3 over x times n2 plus f2 over x minus f1 over y, and 3, and all these multiply the derivative of u and the derivative of b. So this is only transforming this surface integral in the xyz space to the same integral, but now in the uv plane. So that what this is allowing us is to transform the evaluation of this vector function, of the curl of this vector function multiplied by the normal vector of this surface, to a line integral of the contour of this given surface, evaluated as a line integral, as a closed curve line integral of the given vector function times the derivative of the parametric representation of the given surface. So this allows us to make a easier evaluation of the integral. So now we have two different maybe call it transformations of integrals, we can transform a surface integral into a line integral, or vice versa, and a triple integral over of a space in the over a specific space of a region in a space into a surface integral evaluated at this surface S, making this kind of evaluations much more easier.